Hello, my friend, and welcome. Tonight, we're drifting into the science of black holes, the darkest and most mysterious objects in the universe, in a calm, gentle way designed to help you relax, let go of the day, and slowly fall asleep. Chapter 1. What a black hole really is. A black hole is one of the most misunderstood objects in science, partly because its name creates the wrong picture in the mind. It is not a hole in the ordinary sense. It is not an opening into empty nothingness, and it is not a tunnel punched through the universe like a wound in space. A black hole is better understood as a region where matter has been compressed so strongly and gravity has become so intense that once something passes a certain boundary, it cannot get back out again. That boundary is called the event horizon. It is not a hard surface like stone or metal. It is a limit in space-time, a point of no return. To understand why such an object can exist, it helps to begin with gravity itself. In everyday life, gravity seems simple. It pulls apples downward, holds oceans to Earth, and keeps planets in orbit. But in modern physics, gravity is not just a force reaching invisibly across space. In Einstein's description, gravity is the shape of space-time itself. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. A star, a planet, or a galaxy changes the geometry around it simply by existing. Most of the time, this curvature is gentle enough that life proceeds quietly. We stand, walk, breathe, and sleep inside it without noticing. A black hole is what happens when that curvature becomes extreme. If enough mass is packed into a small enough region, space-time bends so deeply that all possible paths inside a certain boundary lead inward. Even light, which normally travels at the fastest speed nature allows, cannot escape once it crosses that boundary. This is why black holes appear black. They do not shine by themselves, because no light from inside the event horizon can reach outside observers. The darkness of a black hole is not the darkness of emptiness. It is the darkness of imprisonment. Light is still light there. Space and time are still space and time. But the geometry has become so severe that escape is no longer part of the future. That detail matters because it corrects one of the oldest misconceptions. A black hole does not suck in everything around it like a cosmic vacuum cleaner. If the sun were somehow replaced by a black hole of the same mass, Earth would not suddenly be dragged inward. It would continue orbiting, because from far enough away, the gravity would be determined by the same total mass. The great difference would not be at Earth's distance, but close to the object itself. Near the event horizon, the curvature becomes extraordinary, and motion changes in ways that no ordinary star could produce. So a black hole is not dangerous merely because it exists. It becomes dangerous when something goes too near. This also means that black holes are not impossible violations of nature. They are not tears in the laws of physics. On the contrary, they emerge from those laws. General relativity predicts that if enough mass collapses inward and no known pressure can resist that collapse, a black hole can form. In that sense, black holes are not science fiction intrusions into the universe. They are one of the most serious and elegant consequences of the physics we already use to describe stars, galaxies, light, and motion. The simplest black hole has several features that are useful to picture. The most famous is the event horizon, the spherical boundary around a non-rotating black hole. From outside, this horizon marks the place beyond which signals cannot return. An outside observer never receives information from deeper than that boundary, In that practical sense, the horizon is what makes the black hole a black hole. Deeper in, according to classical general relativity, lies the singularity, a region where the mathematics indicates that density becomes extreme and the known description breaks down. Scientists do not treat that breakdown as a sign that anything can be imagined there freely. Rather, it tells us that our present theories are incomplete under such extreme conditions. The singularity is not a well-understood object. It is more like a warning that general relativity, by itself, cannot be the whole story. That is why black holes are so important in science. They are not only fascinating cosmic objects, they are meeting points between theories. General relativity describes gravity with astonishing success on large scales. Quantum physics describes matter and radiation with astonishing success on small scales. But inside the deepest black hole environment, those two great frameworks are pushed toward one another. Black holes sit at the edge of our understanding and quietly ask whether the universe is built from principles even deeper than the ones we already know. Still, much of what makes black holes real does not depend on those deepest mysteries. Their existence is strongly supported by observation. We see stars orbiting invisible massive objects at the centers of galaxies. We detect intense radiation from hot matter spiraling inward in accretion disks around compact dark objects. We have recorded gravitational waves produced when black holes merge, sending ripples through space-time itself. We have even obtained images of the dark central shadow region associated with supermassive black holes using global networks of radio telescopes. So although the interior remains hidden, black holes are not speculative fantasies. They are part of the observed universe. Another misconception is that black holes are giant, empty mouths waiting to swallow everything forever. In reality, many black holes are surprisingly ordinary from a distance. They do not roam the cosmos hunting. Most simply sit where gravity and history have placed them. Some are remnants of massive stars that collapsed after exhausting the fuel that once pushed outward against their own weight. Others, especially the supermassive ones found in galactic centers, grew over immense spans of time by accreting gas, swallowing stars, and merging with other black holes. Their presence is dramatic, but their behavior still follows physical rules. They influence their surroundings through gravity, through the heating of matter falling toward them, and sometimes through powerful jets launched from the regions near them. Yet none of this requires black holes to be magical or alive. Their power comes from geometry, mass, motion, and energy. It is also worth pausing on the phrase "point of no return," because it can sound more violent than it really is. If an astronaut were falling toward a sufficiently large black hole, crossing the event horizon would not necessarily feel like hitting a wall. There is no painted line in space, no sudden flash, no cosmic border guard. The event horizon is not locally special in that way. Its importance is global, not tactile. What changes is the structure of possible futures. Before crossing, there are paths that lead outward. After crossing, every path leads deeper in. The horizon is remarkable not because it feels dramatic in the moment, but because it changes what the universe allows next. That idea is difficult because human intuition was built in gentle environments. We are used to thinking of space as a stage and time as a clock. A black hole reminds us that the stage can bend and the clock can warp. Near a black hole, time passes differently than it does farther away. Light loses energy climbing outward. Orbits can tighten until they no longer remain stable. Space behaves not like an empty container, but like a dynamic structure whose shape matters. In that sense, a black hole is not merely an object sitting in space. It is a region where the architecture of reality becomes impossible to ignore. And yet, for all their strangeness, black holes are deeply connected to familiar cosmic processes. They are born from stars, fed by gas, shaped by gravity, and observed through radiation and motion. They belong to the same universe as sunlight, dust clouds, planets, and people. Their mystery comes not from being outside nature, but from revealing how much nature can do when pushed to extremes. A black hole is what happens when mass, gravity, and space-time are allowed to express themselves without compromise. Perhaps that is the most useful way to end a first encounter with the subject. A black hole is not a monster hiding in the dark. It is a natural consequence of a lawful universe, a place where the rules do not disappear, but become more profound. It is darkness made not from absence, but from gravity so complete that even light must surrender to it. And as you let that thought settle, there is something strangely calming in it too. Even the most extreme objects in the cosmos are not chaos without meaning, but part of a universe that remains ordered at every scale. So for now, you can let the day grow quiet and rest in the comfort that even in the deepest darkness, the universe is still following its gentle, consistent laws. Chapter 2. The world before black holes were accepted. Long before black holes became familiar in documentaries, textbooks, and observatory press releases, they lived in science as uneasy ideas. They did not begin as famous cosmic monsters. They began as a question hidden inside gravity itself. If gravity can pull on ordinary matter, and if light is somehow subject to gravity too, could there exist an object so compact that light would never get away? That possibility appeared astonishingly early, long before relativity, long before modern telescopes, and long before anyone had a physical picture of curved space-time. In the late 18th century, Jean Michel in Britain, and later Pierre-Simon Laplace in France, both considered the possibility of bodies so massive and compact that light could not escape them. Their reasoning was framed in the older language of Newtonian gravity and a particle-like view of light, so these objects were not black holes in the modern sense. But the seed of the idea was there. Nature might contain dark stars whose presence could be known only through their gravitational influence on nearby bodies. That early idea did not take hold. Part of the reason was that physics itself was changing. During the 19th century, the wave description of light became more persuasive, and the old Newtonian image of light as a stream of particles behaving like thrown projectiles lost much of its authority. Once that happened, Michel's and Laplace's reasoning no longer seemed compelling. Their dark stars were tied to assumptions that no longer looked secure. So the concept faded, not because it had been decisively disproved, but because the framework that had given rise to it was no longer the framework physicists trusted. The idea lingered in the background of intellectual history, but it did not become a living scientific subject. The modern path toward black holes began only after gravity itself was reimagined. In the early 20th century, Einstein's general theory of relativity replaced the older picture of gravity as a force acting across space with a new vision in which mass and energy shape space-time. That change was not a small correction. It rewrote the stage on which motion occurs. Soon after Einstein published the theory, Karl Schwarzschild found an exact solution, describing the space-time around a spherically symmetric mass. Buried in that solution was a remarkable boundary later associated with the event horizon. But at the time, this was not greeted as a clear prediction that real stars could collapse into real black holes. It looked strange, mathematically delicate, and in many minds, physically suspect. The relevant feature in the equations was often treated as a singularity of the coordinates, rather than an invitation to imagine actual collapsed objects in nature. This hesitation is one of the most important parts of the story. Scientific ideas do not become accepted merely because equations permit them. They must also seem physically meaningful, and that meaning is often shaped by the habits of the scientific community. Einstein himself was uneasy with the notion that nature would truly produce these extreme objects. More broadly, many physicists of the first half of the 20th century were reluctant to embrace solutions that seemed pathological or unreachable in the real universe. The deeper consequences of general relativity were intellectually impressive. But relativity was for a long time less central to mainstream physics than quantum theory, nuclear physics, and later particle physics. Black holes were therefore not rejected in some single dramatic act. They were postponed, treated as exotic edge cases, or quietly set aside. The story sharpened in the late 1930s. In one paper, Einstein argued against the physical reality of what were then called Schwarzschild singularities. Around the same time, J. Robert Oppenheimer and Hartland Snyder studied continued gravitational collapse and showed that, under the assumptions of general relativity, a sufficiently massive collapsing star would not necessarily find a stable final state. Instead, collapse could proceed in a way that cut the object off from the outside universe behind a horizon. In modern hindsight, this paper stands as one of the great conceptual turning points in the history of black holes. But at the time, it did not transform the field overnight. World events soon overtook much of theoretical physics, and attention shifted toward war work, nuclear research, and other urgent subjects. The idea existed, but it did not yet dominate astrophysical thinking. There was also a deeper reason for resistance. Black holes seem to embody an uncomfortable combination of extreme geometry and observational invisibility. Astronomers are more naturally drawn to things that shine, pulse, explode, or leave obvious traces across the sky. A black hole, by definition, does not emit light from within its defining boundary. To accept black holes as real required confidence that invisible objects could be identified through indirect evidence alone. Today, that seems normal, because much of modern astronomy relies on inference. But historically, inference had to earn trust. Before the rise of high-energy astrophysics, radio astronomy, sensitive X-ray observations, and precise orbital measurements, the universe offered fewer ways to expose something so compact and so dark. The concept therefore remained caught between mathematical elegance and observational frustration. Even the language was unsettled. For a long time, physicists used phrases like gravitationally completely collapsed object, which is accurate but hardly memorable. The term black hole became widely associated with John Wheeler in the late 1960s, helping give the subject a more vivid identity. A name does not prove a thing exists, but it can make a concept easier to hold in the mind and easier to discuss across subfields. Wheeler was also part of a broader revival of interest in general relativity during the post-war period. when the subject began to reconnect with observation and with the larger ambitions of fundamental physics. In that environment, black holes gradually moved from mathematical curiosities toward candidate astrophysical realities. What finally began to change scientific opinion was not rhetoric, but evidence. As astronomers opened new observational windows beyond visible light, they started seeing phenomena that ordinary stars struggled to explain. X-ray astronomy was especially important. Gas falling toward a very compact massive object can become extraordinarily hot and radiate intensely in X-rays. Once detectors above Earth's atmosphere began surveying the sky, astronomers found sources of high-energy radiation that hinted at extreme compact objects in binary systems. Among the most famous was Cygnus X1, discovered in the 1960s and identified over the following years as the first major black hole candidate. Its compact object appeared too massive to be a neutron star, while its size constraints and energetic behavior pointed strongly toward a black hole interpretation. By the early 1970s, much of the astronomical community had come to regard Cygnus X1 as the strongest case yet that black holes were not just permitted by theory, but present in nature. Acceptance still came gradually. Scientists are careful, and rightly so. A single candidate does not settle an entire category of objects, but black hole evidence kept accumulating. The centers of galaxies revealed compact dark masses far too large and dense to be ordinary stellar clusters. Quasars and active galactic nuclei showed that enormous amounts of energy could be released by matter falling into deep gravitational wells. Over time, the hypothesis that supermassive black holes sit in galactic centers became not merely plausible but central to galaxy evolution. What had once looked like an improbable theoretical corner began to appear as a common feature of the universe. The final transformation from suspicion to broad acceptance came through convergence. Different methods began pointing in the same direction. Orbital measurements of stars near the center of the Milky Way revealed an unseen central mass packed into a tiny region. Gravitational wave observatories later detected the space-time ripples from merging black holes, directly tracing events that matched relativistic predictions with extraordinary precision. The Event Horizon Telescope then imaged the dark silhouette associated with a supermassive black hole, giving the public a visual icon for an idea that had once seemed almost too abstract to believe. By then, the world before black holes were accepted had truly ended. The objects themselves had not changed. What changed was our ability to read the universe closely enough to stop doubting what the equations had long been hinting at. What makes this history so compelling is that it was never just a march from ignorance to knowledge. It was also a lesson in scientific patience. Black holes were not embraced the instant they were imagined, nor the instant the mathematics allowed them. They passed through stages of suggestion, doubt, neglect, reinterpretation, and finally evidence. The universe did not hurry to make them obvious to us. We had to build better theories, better instruments, and better habits of inference before these invisible objects could become part of accepted reality. And perhaps that is part of their deeper meaning. For a very long time, black holes existed at the edge of thought, where reason could point, but certainty could not yet follow. There is something quietly humbling in that. The universe was under no obligation to reveal its darkest structures quickly. And yet, little by little, it did. So as the day begins to loosen its grip, you can rest with that thought. Some truths remain hidden for a long time, not because they are unreal, but because reality is often deeper than our first way of seeing it. Chapter 3. How black holes are born from dying stars. A stellar black hole is not born in darkness alone. It begins its life in brilliance inside a massive star that spends millions of years holding itself together through a careful balance between gravity and pressure. Gravity is always trying to pull the star inward. At the same time, the star's hot core produces outward pressure through nuclear fusion, the process that turns lighter elements into heavier ones and releases energy. For most of a star's life, these two tendencies oppose one another in a kind of uneasy truce. The star shines because this balance holds. Its light is the visible sign that collapse has, for the moment, been delayed. The story of black hole birth begins when that delay can no longer continue. Massive stars live differently from stars like the Sun. Because they contain far more matter, the pressure and temperature in their cores rise to much greater extremes. That allows them to burn through nuclear fuel far more quickly. A very massive star does not enjoy a longer life because it has more fuel. In a sense, it behaves more extravagantly, consuming that fuel at a much faster rate. As long as fusion continues in the central regions, the star can resist its own gravity. But this resistance is temporary. Fusion depends on having the right conditions and the right fuel, and the sequence cannot continue forever. Over time, the core becomes richer in heavier elements, and the star moves through progressively more advanced stages of burning. Each stage is shorter than the last. The star is not becoming calmer as it ages. It is moving toward instability. Eventually, the core reaches a fatal point. In very massive stars, fusion can build up elements until an iron-rich core forms. This matters because iron does not provide the same life-saving support that earlier fusion stages did. Fusion of lighter elements can release energy and help support the star against gravity, but iron marks a kind of dead end for ordinary stellar burning. Once the core becomes dominated by iron-like material, the star loses its most important defense. The inner engine weakens. Outward pressure falls behind. Gravity, which had been waiting the whole time, begins to win. When the balance fails, the collapse is sudden. The core does not slowly sag inward over ages. It contracts catastrophically. Under these extreme conditions, electrons are forced into protons, producing neutrons and neutrinos. The matter in the inner core becomes extraordinarily dense in a very short span of time. In some cases, the central region stiffens enough that the infalling outer core slams into it and rebounds. That rebound helps launch a shock wave outward through the star. If the explosion succeeds, the outer layers are blasted into space in a core collapse supernova. The sky briefly gains one of the most dramatic events in nature, not because the star has found new strength, but because its inner structure has failed so completely that collapse and explosion become part of the same final act. What remains after that explosion depends on how much mass is left concentrated in the collapsed core. This is the crucial branching point. If the remnant core is not too massive, neutron pressure and related nuclear effects can hold it up as a neutron star. A neutron star is already an astonishing object, with matter compressed to densities far beyond anything in ordinary experience. But there is a limit to how much even that extreme state can support. If the collapsed core is massive enough, no known pressure can permanently stop further collapse. In that case, the core continues inward until a black hole forms. The star's visible life ends, but its gravity leaves behind something more compact and more extreme than any normal star could ever become. This does not mean every massive star produces a bright classical supernova followed by a neat black hole remnant. Real stellar death can be messier than that simplified picture. In some cases, the outward explosion may be weak. In others, material blasted outward may not fully escape and can fall back onto the remnant, adding enough mass to push a neutron star-like core past stability and into black hole formation. There are also scenarios in which the collapse may proceed with little visible fireworks compared with the most dramatic supernovae. Astronomers sometimes discuss failed supernovae, where a massive star may dim and disappear with much less luminous explosion than people expect. The exact details depend on internal structure, mass loss during the star's life, rotation, composition, and the complicated physics of collapse and shock revival. So black hole birth is not one single theatrical script repeated the same way each time. It is a family of endings shaped by how the star lived before it died. Rotation can matter greatly in these endings. Stars are not always perfectly still spheres. They rotate, sometimes rapidly, and that rotation can influence how collapse unfolds. Angular momentum may help form a disk of infalling matter around the newly formed black hole, rather than allowing everything to plunge straight inward at once. Under certain conditions, especially in very rapidly rotating massive stars, this can be connected to highly energetic outflows and perhaps even some forms of gamma-ray burst activity. This is still an area where models remain complex and details depend on initial conditions, but the central idea is clear. The death of a massive star is not governed by mass alone. Motion matters too. The manner in which the star spins, sheds mass, and interacts with companions can shape the kind of remnant it leaves behind. Companion stars can alter the story further. Many massive stars are born not in solitude but in binary systems. A star that might not have formed a black hole on its own can lose material to a companion or gain material, or evolve under tidal influences that change its spin and internal structure. Later, if a black hole does form in such a system, the remnant may continue interacting with the companion by drawing gas from it. That gas can heat enormously as it spirals inward, producing X-rays and making the black hole detectable even though the black hole itself emits no light from within its horizon. This belongs more to the next phase of black hole life than to its birth. But it reminds us that stellar death is often shaped by relationship, not isolation. A star's ending may depend not only on what it is, but on what has been orbiting beside it. It is also important to be careful with thresholds. Popular summaries often state simple dividing lines such as one mass range yielding neutron stars and another yielding black holes. These summaries are useful introductions, but nature is more subtle. The final outcome depends not merely on the star's birth mass, but on how much matter it loses through winds, how metals affect that mass loss, how rotation redistributes material inside the star, and how much mass remains in the core when collapse begins. For that reason, astronomers do not speak of black hole birth as though it were determined by one number alone. It is a competition among structure, history, and gravity. That is part of why stellar evolution remains an active field rather than a solved diagram in a classroom. There is something especially striking about the fact that a black hole begins inside an object whose earlier life was devoted to preventing collapse. For most of its existence, A massive star is a machine of resistance. It creates heat and pressure from fusion precisely so that gravity does not crush it. Its brilliance is the cost of staying open against inward fall. But that resistance carries within it the seeds of its ending. Each stage of fusion changes the core, bringing the star closer to a state in which further support becomes impossible. The same processes that keep the star alive also prepare the conditions for its failure. A black hole is born not from some accidental interruption of the laws of nature, but from the long, faithful working out of those laws across the life of a star. And yet the result is not simply destruction. When a massive star dies, it also enriches the universe. Material expelled in supernova explosions becomes part of future clouds, future stars, future planets, and eventually future living things. Even when collapse leads to a black hole, the surrounding event can seed the cosmos with heavy elements made in stellar interiors and explosive processes. In that sense, black hole formation belongs to a larger cycle. It is an ending for one object, but also part of the ongoing chemical and gravitational evolution of the universe. The death of a massive star does not erase its history. It redistributes it. So when we picture a black hole being born from a dying star, we should not imagine a simple act of disappearance. We should imagine a long tension finally resolved. For millions of years, gravity pressed inward while fusion pushed outward. Then the fuel changed, the support weakened, and nature crossed a threshold from star to remnant. Sometimes that remnant is a neutron star. Sometimes it is a black hole. In either case, the transition is one of the great transformations in astrophysics, where the visible radiance of a star gives way to one of the darkest and most powerful objects the universe can create. There is a quiet reflection hidden in that process. A star can spend nearly all of its life holding itself open against collapse, only for its final truth to emerge in a brief and violent surrender. And still, from that ending, the universe makes new structure, new matter, and new futures. Perhaps that is one of the gentlest lessons in the life cycle of stars. Even the deepest collapse is not outside the order of things, but part of the same vast continuity that carried the star from first light to final darkness. Chapter 4: Inside the Structure of a Black Hole. When people imagine the inside of a black hole, they often picture it as a kind of cosmic cavern, a dark, hollow place with walls, depth, and perhaps some hidden chamber at the center. But that picture is misleading. A black hole is not like a cave in space. It is a region defined by geometry, and its structure is not built from surfaces and rooms, but from boundaries, trajectories, and the way space-time itself is arranged. To understand the structure of a black hole, it helps to begin with an unusual fact. From the outside, a black hole is in some ways one of the simplest objects in the universe. Once a collapsing object settles down, the external black hole is described by only a small set of basic properties, chiefly its mass and spin, with electric charge expected to be negligible in most astrophysical cases. That simplicity is one of the most surprising things about black holes. A star may begin as a complex body of layered gases, magnetic fields, turbulence, and nuclear reactions, but the black hole left behind is far more stripped down in its outward description. The first key structural feature is the event horizon. This is not a material shell. It is not a hard crust, and it is not a membrane you could knock on. It is a boundary in space-time marking the limit beyond which light and any other signal can no longer escape to the outside universe. That is what makes a black hole black, in the most literal scientific sense. The event horizon separates the region that can still communicate outward from the region that cannot. In the simplest, non-rotating case, this horizon is spherical. Its size depends on the mass of the black hole, so a more massive black hole has a larger horizon. From far away, the horizon can be thought of as the outermost defining edge of the black hole, even though it is not a physical surface in the ordinary sense. This leads to an important distinction between the black hole itself and the glowing structures people often see in illustrations. The bright ring or swirling disk shown in many images is usually not the black hole proper. It is matter outside the horizon, heated to extreme temperatures as it falls inward. NASA describes the accretion disk as the main light source associated with a black hole, and notes that matter gradually moves from the outer disk toward the inner edge before crossing the event horizon. The disk can shine brilliantly, while the black hole remains dark. This distinction matters because it reminds us that the structure of a black hole includes both what is directly part of the black hole and what only surrounds it. The disk belongs to the environment, not to the black hole's interior anatomy. Just outside the horizon, gravity bends light so strongly that the region becomes visually and physically strange. Light can be deflected, trapped on unstable paths, or redirected toward distant observers. This is why images of black holes show a dark central area larger than the horizon alone might suggest. The silhouette seen by the Event Horizon Telescope is shaped by the extreme bending of light around the black hole, with glowing gas outlining a dark center. The apparent structure is therefore not just a simple edge, but a combination of the horizon, the surrounding hot gas, and the curved paths that light can take near such intense gravity. In this sense, the visible appearance of a black hole is partly an optical consequence of space-time geometry. If one moves conceptually inward past the horizon, classical general relativity says that all future directed paths lead deeper into the black hole. This is one of the hardest ideas to picture because it is not simply a matter of being pulled harder in the ordinary way. Inside the horizon, going inward is not like choosing a direction among many. It becomes part of the causal structure of space-time itself. The center lies ahead in the same unavoidable sense that tomorrow lies ahead in ordinary life. This is why returning outward is not just difficult, but impossible within classical relativity. The black hole interior is not merely a place where escape is unlikely. It is a place where the structure of the future has changed. At the center of the simplest classical black hole model lies the singularity. In the standard description, this is the region where density and spacetime curvature are driven beyond the limits of the theory. Britannica describes the singularity as the center of the black hole, hidden by the event horizon. But physicists treat this carefully. The singularity is not understood as a well-mapped physical object in the way a planet or a star's core is understood. Rather, it signals that classical general relativity has reached a boundary where quantum effects should become important, and the older theory alone cannot provide a complete description. Preskill makes this point directly, noting that deep inside a black hole, quantum effects become important, and classical general relativity cannot predict what happens. So the singularity is both part of the classical structure and a sign that our present picture is incomplete. The simplest version of this story describes a non-rotating black hole sometimes called a Schwarzschild black hole. But real astrophysical black holes are expected to rotate, often substantially, because the stars and matter that form them carry angular momentum. Rotation changes the structure in important ways. A spinning black hole still has an event horizon, but the geometry around it becomes more complex. Space-time is dragged around by the rotation itself, a phenomenon known as frame dragging. In practical terms, this means that the black hole does not merely sit in space-time as a passive sink. Its spin twists the surrounding geometry. The result is that the structure of a rotating black hole is not just a spherical boundary around a dark center. It includes additional regions shaped by spin, and the motion of matter and light nearby becomes correspondingly richer. One of the most important outer features of a rotating black hole is the ergosphere, a region outside the event horizon where space-time is dragged around so strongly that nothing can remain truly at rest relative to distant observers. This does not mean everything is immediately swallowed, because the ergosphere lies outside the horizon, and escape is still possible from it. But it does mean that the black hole's spin changes what kinds of motion are allowed nearby. The ergosphere is especially interesting because, in principle, energy can be extracted from black hole rotation through processes that take advantage of this dragged space-time. So in spinning black holes, structure is not only about where things cannot escape, but also about where motion itself is compelled into new patterns. The interior of a rotating black hole is also theoretically different from that of the simplest non-rotating case. In idealized mathematical solutions, the central singularity is not described the same way as in the spherical case, and additional horizons can appear in the equations. But here caution is essential. These deeper interior features belong to exact solutions under highly ideal assumptions, and physicists do not treat them as fully settled descriptions of real astrophysical interiors. Perturbations in falling matter and quantum effects may alter the story substantially. So while the mathematics of rotating black holes is extraordinarily rich, the most reliable structural picture for general understanding remains this. A rotating black hole has an event horizon, a region of dragged space-time outside it, and an interior that classical relativity describes only up to the point where the theory itself begins to fail. Another profound aspect of black hole structure is how little of the original object remains visible from outside. Physicists sometimes summarize this with the phrase that a black hole has no hair, meaning that once it settles down, most of the detailed information about the collapsing body is no longer accessible to an outside observer. The original star may have had layers, chemistry, asymmetries, and complicated internal activity, but the final black hole is outwardly much simpler. This does not mean the underlying problem of information is solved. In fact, it leads directly into one of the deepest questions in modern physics. But as a statement about classical external structure, it captures something real. Black holes are remarkably spare objects. Their anatomy is defined by geometry more than by material complexity. So if we gather the pieces carefully, the structure of a black hole becomes clearer. There is the event horizon, which defines the boundary of no return. There is the surrounding space-time where light bends and motion becomes extreme. There may be glowing matter outside, but that belongs to the black hole's environment, not to the black hole itself. And there is an interior that, in classical theory, ends in a singularity, while also pointing toward the need for a deeper union of gravity and quantum physics. In spinning cases, the structure becomes even richer through frame dragging and the ergosphere, showing that black holes are not merely dark spheres, but precise and dynamic geometrical objects. There is something quietly unsettling in this simplicity. One of the most extreme things in the universe is also one of the cleanest in form, as though nature sometimes removes detail not by erasing reality, but by pushing it to a deeper level we cannot yet fully read. And perhaps that is part of the strange calm of black holes. Behind all the violence that forms them, what remains is an object defined by a few silent features, waiting at the edge of what thought can presently reach. Chapter 5. Spinning black holes and the strange physics around them. A black hole that spins is not merely a darker version of a simpler object. Its rotation changes the geometry around it and makes the surrounding region far stranger than the basic picture of a quiet spherical black hole might suggest. In the classical description, an isolated black hole is characterized mainly by its mass and spin, with electric charge expected to be negligible in ordinary astrophysical settings. That means spin is not a small secondary detail. It is one of the most fundamental properties a real black hole can have. And because most stars, gas clouds, and compact remnants rotate before collapse, astronomers expect many real black holes to rotate as well. A spinning black hole is therefore not an exotic exception. It is likely close to the norm in the universe. The reason spin matters so much is that general relativity does not treat empty space around a massive body as a passive stage. A rotating mass changes the behavior of space-time itself. Around a spinning black hole, the surrounding geometry is dragged into motion, an effect known as frame dragging. The idea was not invented specifically for black holes. It is a prediction of Einstein's theory more generally, and it was tested around Earth by the Gravity Probe B mission, which measured the subtle way a spinning body drags local space-time around with it. Near a black hole, however, this effect becomes immensely stronger. Rotation no longer produces only a delicate correction. It becomes a defining feature of the environment, shaping how matter moves, how light travels, and even which states of motion remain possible near the hole. This is why the space around a spinning black hole cannot be thought of as still. Even before anything crosses the event horizon, the black hole's rotation is already influencing the region outside it. In the simplest non-rotating case, one can still imagine an outside observer who hovers at a fixed position if enough support is provided. But around a spinning black hole, the dragging of space-time becomes so intense near the hole that certain notions of staying still stop making physical sense. The geometry itself is being twisted. Matter and radiation in the inner regions respond not only to gravity pulling inward, but to the rotating structure of space-time through which they move. In that sense, a spinning black hole does not simply sit in the cosmos. It imposes a kind of whirl upon the arena around it. One of the most distinctive regions created by this rotation is the ergosphere. This lies outside the event horizon, which means it is not yet the true point of no return. Escape from the ergosphere is still possible. But inside this region, frame dragging becomes so strong that no object can remain at rest with respect to a distant observer. Everything is compelled to move in the same general direction as the black hole's spin. This does not mean everything immediately falls inward. Rather, it means that the black hole's rotation changes the menu of allowed motion. The ergosphere is one of the great examples of how black holes alter possibility itself. Around a spinning black hole, motion is not simply a matter of free choice and initial speed. The geometry has already begun to decide part of the answer. The ergosphere is scientifically fascinating for another reason as well. In principle, rotational energy can be extracted from a spinning black hole. This idea, associated with the Penrose process in theoretical work, arises because the ergosphere is not just a region of distorted motion, but a region where the black hole's spin has made energy bookkeeping more subtle than in ordinary space. The exact mechanisms that matter in real astrophysical systems are usually more complicated than the ideal thought experiment itself, involving magnetic fields and hot plasma rather than neatly arranged particles. Still, the basic insight remains important. A spinning black hole is not only an absorber. Under the right conditions, its rotation can help power phenomena outside it. This gives black hole spin a dynamic role in astrophysics, rather than leaving it as a passive label attached to the object. That role becomes especially important when matter is falling toward the black hole. Gas pulled inward does not usually plunge straight down in a simple radial way. Instead, it tends to form a hot, rapidly rotating accretion disk outside the event horizon. Near spinning black holes, the structure and behavior of this inner disk can be strongly affected by the hole's rotation. NASA's black hole anatomy materials note that the main light source around a black hole is the accretion disk, while the Event Horizon Telescope emphasizes that the visible appearance near a black hole depends mostly on mass and, to a lesser degree, spin. The spin can influence the inner flow, alter the geometry of the emitting region, and affect how close stable orbits can exist to the hole. In practical terms, a fast spin can allow matter to orbit deeper in the gravitational well before plunging inward, which changes how much energy can be released on the way down. This is one reason astronomers care so much about measuring spin. The rate at which a black hole rotates contains information about its history. A black hole may gain spin from the rotation of the star that collapsed to form it, from long-term accretion of matter that spirals incoherently, or from mergers with other compact objects. ESA notes that a very rapid rotation can reflect either sustained feeding through an accretion disk or past merger history. In that sense, spin acts almost like a memory of formation. The black hole itself looks simple from the outside, but its spin may preserve clues about the path it took to become what it is. When astronomers estimate spin from X-ray observations of inner disks or other signatures, they are not just measuring a present property. They are reading a compressed record of astrophysical experience. Spinning black holes are also deeply connected with some of the most dramatic jets in the universe. Not every black hole produces strong jets, and the exact mechanism remains an active field of research. But NASA notes that in black holes of many sizes, a small fraction of material near the inner edge of the accretion flow can be redirected into oppositely directed particle jets moving at nearly the speed of light. Numerical studies and observational interpretations have long suggested that spin can be important here, especially when strong magnetic fields thread the inner flow. Event Horizon Telescope science materials note that when a spinning black hole accretes hot plasma, strong magnetic fields can develop around the spin axis. NASA simulation work further indicates that in rotating cases, jets can form closer to the ergosphere, and magnetic fields can be strongly twisted by frame dragging. So although the full engine is complex, the broad picture is clear. Spin may help organize some of the most powerful outflows known in astrophysics. Rotation can also make black hole systems geometrically untidy. The spin axis of the black hole does not always line up perfectly with the orbit of a companion star or the outer accretion flow. In such cases, the inner disk may tilt, warp, or precess, and the jets associated with the inner region may change direction over time. ESA observations of systems such as V404 Cygni have been interpreted in this way, with the inner flow wobbling and causing the jet orientation to vary. This reminds us that a spinning black hole is not always surrounded by a neat, flat, textbook disk. Real systems can be misaligned and time-dependent. The result is a kind of astrophysical choreography in which spin, infall, magnetic structure, and geometry interact continuously. The black hole remains simple in its core description, but the physics around it can become beautifully complicated. Even the light escaping from near a spinning black hole carries strange signatures of rotation. Near the inner disk, matter can move so rapidly that relativistic beaming becomes important, making one side of the flow appear brighter and bluer, while the opposite side appears dimmer and redder. NASA's black hole anatomy description highlights this asymmetry and connects it to the enormous speeds reached in the inner accretion flow. The black hole's spin does not act alone here, but it helps determine the structure of the region where such extreme motion occurs. The visible image near a spinning black hole is therefore not a simple photograph of an object. It is a highly processed consequence of curved space-time, rapid orbital motion, light bending, and the geometry of emission. What we see is not merely matter sitting near darkness. It is the universe translating extreme gravity into patterns of light. For all this complexity, there is also a curious elegance to spinning black holes. Rotation introduces richness, but not disorder. The strange physics near them is still lawful physics. Frame dragging, the ergosphere inner disk behavior, tilted flows, high-energy radiation, and jets are not random violations of cosmic order. They are what general relativity and plasma astrophysics naturally allow under extreme conditions. A spinning black hole seems dramatic because it pushes familiar principles into a regime where our everyday intuition no longer helps. But the drama comes from consistency, not from chaos. The equations do not fail simply because the environment becomes severe. On the contrary, they reveal just how much structure reality can contain when gravity and motion work together at their most intense. Perhaps that is why spinning black holes feel so unsettling and so beautiful at the same time. They show that even emptiness can be set into motion, and that a rotating darkness can organize light, matter, and energy into patterns of extraordinary precision. Somewhere in that idea, there is also a quiet reflection for us. Much of the universe is not still at all, but moving in ways far deeper than the eye can see, and yet it remains ordered. So as this chapter comes to rest, you can leave the day behind with that thought. Even in the strangest regions of existence, reality does not lose its shape. It simply becomes more profound. Chapter 6. What happens to time near a black hole? One of the strangest truths about black holes is that they do not merely affect where things go. They affect when things happen. Near a black hole, time itself does not pass in the same way it does far away. This is not a metaphor, And it is not just a visual illusion created by dramatic storytelling. It is a real prediction of general relativity. Clocks in stronger gravitational fields run more slowly relative to clocks farther away. Britannica's overview of relativity describes this as gravitational time dilation, and NASA's black hole materials explain that time passes more slowly closer to a black hole than farther from it. This idea can feel unnatural because ordinary life teaches us to think of time as universal. We are used to imagining that there is one shared flow of moments, the same for everyone, whether they are standing on the ground, flying in an airplane, or looking up at the night sky. Relativity replaces that comforting simplicity with something deeper. Time depends on motion and gravity. A clock is not measuring some separate cosmic river outside the universe. It is part of the universe, and its rate is shaped by the conditions in which it exists. The stronger the gravitational field, the more stretched the passage of time becomes relative to regions where gravity is weaker. Around a black hole, this effect becomes extreme because the curvature of space-time becomes extreme. A distant observer watching a clock descend toward a black hole would see that clock tick more and more slowly. The light coming from it would also be shifted to lower frequencies, becoming redder and harder to detect. Educational astronomy sources describe this picture very directly. To a distant observer, anything approaching the event horizon appears to slow down, dim, and redshift. The object does not seem to cross the horizon in a clean, ordinary way. Instead, its visible signals fade and stretch as though time itself were being pulled thin. That outside view is only half the story, though, because the falling observer does not experience the same thing. Someone falling freely toward a sufficiently large black hole would not feel their own time stopping. Their wristwatch would tick normally to them. Their heartbeat, thoughts, and physical processes would continue in the ordinary local way. In relativity, this difference between perspectives is essential. The distant observer says the falling clock slows dramatically near the horizon. The infalling observer says their own local time proceeds normally. Both descriptions are valid because they refer to different reference frames and different ways of comparing events. This is one reason black holes are so mentally difficult. They force us to give up the idea that there is one final viewpoint from which time can be judged absolutely. Near a black hole, asking what really happens to time is incomplete unless one specifies for whom. From far away, the approach to the horizon looks endlessly delayed. From the falling traveler's own perspective, the horizon can be crossed after a finite amount of personal time. The tension between these descriptions is not a contradiction in the theory. It is part of what the theory means. Time is not detached from the observer. It is woven into the geometry of space-time and the path taken through it. Another consequence of gravitational time dilation is gravitational redshift. If light climbs out from a strong gravitational field, it loses energy in the sense relevant to distant measurement, and its frequency is observed to decrease. Britannica explains this connection directly. Time dilation in a gravitational field shifts light toward longer wavelengths. Around a black hole, this means signals from deeper regions appear redder and weaker to distant observers. So the strange behavior of time is not hidden only in abstract clock comparisons. It leaves traces in light itself. Time and light reveal the same geometry in different ways. It is also important to separate what is scientifically established from what is often dramatized in popular culture. People sometimes say that time stops at the event horizon. That is too simple. It is more accurate to say that, from the viewpoint of a distant observer using distant clocks, signals from an object near the horizon become ever more delayed and redshifted. The object appears to asymptotically freeze from that outside perspective. But the object itself does not experience its own time halting at that boundary. General relativity does not describe the horizon as a place where a traveler locally sees their watch stop. The apparent freezing is a relationship between observers, not a universal physical pause. This brings us to a subtle and beautiful point. A black hole changes time not only by slowing clocks near it, but by changing which events can influence which others. The event horizon is a causal boundary. Britannica describes it as the limit beyond which nothing can escape, including light. That means time near a black hole is not merely slower in a quantitative sense. The structure of cause and effect is altered. Some futures remain open outside the horizon, while beyond it all, outward communication is cut off. In that respect, the black hole is not just a place where clocks run differently. It is a place where the architecture of possible futures becomes radically constrained. Observational astronomy gives us reason to take all of this seriously, even though we do not hover clocks just above event horizons. Einstein's theory has been tested in weaker gravitational fields many times, and strong field tests near black holes continue to support it. The European Southern Observatory reported a successful test of general relativity using the orbit of a star passing close to the supermassive black hole at the center of the Milky Way. That particular star was not close enough to the horizon for the most dramatic black hole time dilation effects, but the measurement matters because it confirms relativity's behavior in a much stronger gravitational setting than ordinary solar system tests. Black holes remain one of the most important laboratories for the study of time in strong gravity. Near a spinning black hole, the picture becomes richer still. As strong gravity sources explain, a rotating black hole not only curves space-time, but drags it around with it. This frame dragging affects motion, orbits, and the detailed behavior of matter in the inner accretion flow. The basic fact of gravitational time dilation remains, but it is now embedded in a more complicated geometry, where space and time are intertwined even more deeply. The result is that the region near a rotating black hole is not simply a slower clock version of ordinary space. It is a rotating space-time environment where the measurement of time depends on gravity, motion, and the drag geometry all at once. There is another misconception worth clearing away. Time dilation near a black hole does not mean a person could treat it like a magical time machine in any easy or practical sense. Relativity does imply that different observers can experience different amounts of elapsed time between events. But surviving near a black hole is another matter entirely, and the environment is often hostile because of tidal forces, radiation from hot surrounding matter, and orbital demands. The scientific point is not that black holes offer a convenient way to skip through history. The point is that the passage of time is not fixed by human expectation. Nature allows different histories of elapsed time depending on the path through space-time. What makes this especially profound is that the effect is not unique to black holes. Gravitational time dilation exists everywhere. It has been measured on Earth, and must be accounted for in technologies such as satellite navigation. Black holes simply reveal the principle in its most dramatic form. They take a quiet truth of relativity and push it to an unforgettable extreme. The same universe in which clocks on satellites and clocks on Earth drift slightly apart is the universe in which time near a black hole can diverge enormously from time far away. The principle is continuous. Black holes are not exceptions to the law. They are the place where the law becomes impossible to ignore. There is also a philosophical gentleness hidden inside this severe physics. We often speak as if time were something we move through together in one common stream. But relativity suggests a more subtle reality. Time belongs to relationship. It is shaped by where you are, how you move, and how deeply gravity holds your path. Near a black hole, that truth becomes almost unbearable in its clarity. The universe does not hand out one clock to everything. It lets each world line keep its own account. And perhaps that is why black holes feel so haunting. They remind us that time is not the firm background we once imagined, but part of the living structure of reality itself. Even so, there is calm in that thought too. The universe is stranger than our instincts, yet it is not lawless. Even where time bends toward darkness, it still does so with perfect consistency. So as this chapter ends, you can let the day loosen and drift away, knowing that even in the deepest gravity, the cosmos remains faithful to its quiet order. Chapter 7. The Violent World Around Black Holes. A black hole is dark by definition, but the region around it can be among the brightest and most violent places in the universe. That contrast is one of the most striking things about black hole physics. The black hole itself does not shine from within its event horizon, yet the matter falling toward it can become so hot, so compressed, and so accelerated that it produces enormous amounts of radiation. In many cases, the true drama of a black hole is not hidden inside it, but unfolding just outside the boundary where escape is still possible. This is where gravity, motion, magnetism, and heat combine to create one of the harshest environments known in astrophysics. The first step in this violence is accretion. Black holes do not usually feed by swallowing matter in a perfectly straight plunge. Gas and dust falling inward usually carry angular momentum, which means they cannot simply drop directly into the center. Instead, they spread into a flattened, rotating accretion disk outside the event horizon. NASA's black hole materials describe this disk as a hot, swirling structure in which matter collects, flattens, and gradually moves inward. As the gas circles the black hole, friction-like processes within the disk and turbulent interactions between different layers cause matter to lose orbital energy. That lost energy does not vanish quietly. Much of it is converted into heat, and the disk can become extraordinarily hot and luminous, especially in X-rays. This is why a feeding black hole can outshine entire populations of stars. The energy released does not come from nuclear fusion, as it does in ordinary stars. It comes from gravity. Matter falling deeper into the black hole's gravitational well gives up enormous amounts of potential energy, and the disk radiates that energy outward before the matter finally crosses the horizon. In the case of supermassive black holes at the centers of galaxies, this process can power active galactic nuclei and quasars, some of the brightest persistent sources in the universe. The black hole itself remains dark, but the environment just outside it becomes a furnace of orbiting plasma. The inner parts of the accretion disk are especially severe. There, matter can orbit at a substantial fraction of the speed of light. NASA describes the light from these regions as asymmetric because the gas on the side rotating toward us appears brighter, while the gas on the receding side appears dimmer, an effect produced by relativity. This means the region around a black hole is not merely hot and chaotic. It is also governed by the combined effects of extreme velocity, curved spacetime, and intense radiation. The closer matter gets to the inner edge of the disk, the more the environment departs from everyday physical intuition. Light is bent, time is dilated, and the gas itself behaves more like a relativistic fluid than anything familiar from ordinary experience. There is also a deep instability built into this process. Matter in the disk is not arranged in calm, perfectly circular layers. It is magnetized, turbulent, and constantly redistributing angular momentum. Small disturbances can grow. Density can fluctuate. Brightness can change rapidly. Black hole feeding is therefore often variable rather than steady. Some systems brighten and fade dramatically as the inflow rate changes. Others switch between states in which different parts of the disk and surrounding hot plasma dominate the emission. The violent world around a black hole is not just a matter of extreme conditions. It is a matter of restless conditions, where the entire flow can reconfigure itself on timescales ranging from very short to cosmically long, depending on the mass of the black hole and the structure of the surrounding gas. In addition to the disk, many black holes are surrounded by a hot corona of energetic particles. This is not a corona in exactly the same sense as the outer atmosphere of the Sun, but the analogy is useful because it refers to a region of extremely energetic plasma above and below the disk. High-energy photons from this region can dominate the X-ray emission in some systems. Observations with X-ray telescopes have helped reveal that the environment near black holes often includes this compact, intensely hot source of radiation interacting with the disk below it. The result is an ecosystem of matter and light, with the disk producing one form of emission, the corona reshaping it, and gravity bending it all before it reaches distant observers. Then there are the jets. In some black hole systems, a small fraction of the infalling matter is not swallowed and is not left orbiting in the disk. Instead, it is redirected outward in narrow, oppositely directed streams that shoot away from the black hole along the spin axis at speeds close to that of light. NASA notes that such particle jets can form in black holes of many sizes. These jets are among the most astonishing structures in astronomy because they can remain collimated across huge distances and carry enormous amounts of energy away from the vicinity of the hole. Their exact launching mechanism is complex and remains an active research area. But magnetic fields, rotation, and the inner accretion flow all appear to play crucial roles. In some systems, the violence around a black hole is therefore not confined to a small neighborhood. It can reach outward across the host galaxy and beyond. The violence is not limited to steady feeding. Sometimes a black hole encounters an entire star. If a star passes close enough to a massive black hole, the difference in gravitational pull across the star becomes so strong that the star is torn apart. This is called a tidal disruption event. NASA explains that as an object gets closer to a black hole, the gravitational force intensifies and the matter continues to be pulled apart, a process often described as spaghettification. ESA describes these events as sudden flares produced when a star feels a stronger pull on one side than the other, is disrupted, and streams of stellar debris begin to flow inward. Part of that material may be accreted, while part of it can be flung outward. For a while, a previously quiet galaxy may light up dramatically as the black hole feasts on the remains of a star. These tidal events are particularly important because many supermassive black holes are otherwise dormant most of the time. They sit in galactic centers without a bright, permanent accretion disk. A tidal disruption event briefly reveals them by forcing a sudden episode of feeding. ESA conference materials describe such events as a prime source of information about otherwise dormant black holes. Some disruptions are complete, destroying the star entirely. Others are partial, in which the star survives passage but loses material and may return again, producing repeated outbursts. That means the black hole's violent environment can sometimes be episodic rather than continuous, flaring into visibility only when a star wanders too close. There is another kind of violence associated with black holes that is invisible to ordinary light: gravitational wave emission during mergers. When two black holes spiral together and collide, the final moments release enormous amounts of energy in the form of ripples in spacetime. LIGO materials describe such events as highly energetic phenomena otherwise hidden from us. This is a different kind of violence from hot gas and X-rays because it does not rely on accretion or electromagnetic radiation. It is the violence of motion itself in curved spacetime. In those last instants before merger, the geometry of the universe shakes, and detectors across Earth can register the passage of that disturbance. The environment of a black hole is therefore violent not only when it is feeding, but also when it is dancing fatally with another compact object. Even when no whole star is destroyed and no merger is occurring, the neighborhood around a black hole remains harsh beyond almost any human analogy. Tidal forces near smaller black holes can become intense enough to stretch and compress matter severely. Radiation from the inner disk can be lethal to ordinary matter. Magnetic fields can twist violently. Orbits near the inner region can become unstable. The space around a black hole is not empty peace. It is a place where matter is heated, accelerated, distorted, and sometimes expelled with enormous efficiency. That is why black holes are so influential in astrophysics. They are not merely endpoints of collapse. They are engines that can shape their surroundings through energy release, feedback, and destruction. And yet, what makes this world so powerful is not disorder in the usual sense. The violence around black holes is lawful. The disk forms because angular momentum demands it. The heating happens because energy is dissipated as matter moves inward. Jets emerge through the interaction of rotation, fields, and plasma. Tidal disruption follows from the same gravity that also holds galaxies together. Even the most furious black hole environment is not a break in the logic of nature. It is nature operating at its sharpest edge. There is something quietly humbling in that. Around a black hole, destruction and brilliance can come from the same source, and the brightest light may appear at the edge of the darkest object. Perhaps that is part of the deeper beauty here. The universe does not separate terror from order as neatly as we do. Even in its harshest places, it remains intelligible. And as you let that thought settle, there is a strange calm in knowing that beyond all this violence, the cosmos still moves by consistent laws, as if even its fiercest regions belong to a larger and quieter harmony. Chapter 8: How we actually detect black holes. black holes are among the clearest examples in science of something being known before it is directly seen. For a long time, they existed as consequences of theory, then as strong suspects in observations, and only later as objects supported by several different lines of evidence at once. That history matters because black holes do not reveal themselves in the ordinary way. Since light cannot escape from within the event horizon, astronomers do not usually detect black holes by looking straight at the black hole itself. Instead, they detect the effects a black hole has on its surroundings, on nearby matter, on nearby stars, on passing light, and on space-time itself. In that sense, black hole detection is a science of inference, but it is guesswork. It is evidence gathered from the behavior of the universe around an invisible center. One of the oldest and most powerful methods is to watch how stars move. If a visible star orbits something that emits little or no light, astronomers can use that orbit to estimate the hidden object's mass. If the mass is large enough and packed into a region small enough, familiar alternatives begin to fail. This is especially important in binary systems, where one star may orbit a compact dark companion. If the unseen companion is too massive to be a white dwarf or neutron star, then a black hole becomes the leading explanation. NASA and Hubble science materials both emphasize that black holes can be detected through the way nearby matter and stars dance around them. The orbit becomes the clue. The invisible object writes its presence into the motion of what can still be seen. This same logic extends to the centers of galaxies. At the heart of the Milky Way, for example, astronomers have tracked stars moving on tight, rapid orbits around an unseen central mass. Those observations show that millions of solar masses are concentrated into a very small region, far too compact to be explained by an ordinary cluster of dim stars. That is one of the strongest arguments for a supermassive black hole at our galaxy's center. The black hole is not identified because it glows like a star. It is identified because the surrounding stars behave as if they are circling an object of enormous mass confined to a tiny volume. In other galaxies, the same general method works on larger scales through stellar motions and gas motions measured in galactic nuclei. Another major method is to detect light from matter just before it disappears. A black hole itself does not shine, but gas falling toward it can become extraordinarily hot in an accretion disk. NASA explains that this surrounding matter, not yet inside the event horizon, can emit intense radiation, especially in X-rays. ESA likewise notes that the final stages of infalling matter are especially well studied with X-ray and gamma-ray observatories. This is why many black holes were first identified not by darkness alone, but by violence. Astronomers found compact sources emitting huge amounts of high-energy radiation, then worked backward to infer that the engine had to be a black hole or strong black hole candidate. The invisible object gives itself away by heating nearby matter to extraordinary temperatures. This is particularly useful in X-ray binaries, where a black hole pulls material from a companion star. As that material spirals inward, it forms a disk and radiates strongly. Some of the earliest convincing black hole candidates were found this way. The key is not just brightness, but compactness, temperature, and variability. ESA has pointed out in its black hole observation materials that certain X-ray sources are too bright or too variable to be explained easily by less extreme objects. The radiation changes because the inner flow of matter is unstable, turbulent, and close to the edge of a very deep gravitational well. So astronomers do not merely see a bright source and announce a black hole. They compare the properties of the source with what other compact objects can plausibly do. Black hole detection often works by elimination as much as by direct signature. There's also spectroscopy, which is especially important for supermassive black holes in galactic centers. NASA explains that astronomers can use spectra to distinguish between the signatures of gas moving very rapidly near a black hole and the slower, cooler gas associated with ordinary star formation. This matters because the light from gas contains information about speed, temperature, composition, and motion along the line of sight. When gas near a galactic nucleus is moving extremely fast, its spectral lines broaden in characteristic ways. That broadening can reveal the presence of a deep gravitational potential and a compact central mass. In this way, even when a black hole cannot be imaged directly, the fingerprints of motion in surrounding gas help expose it. The black hole remains invisible, but its gravity reshapes the light of everything near it. A different strategy is to use gravitational lensing. Massive objects bend light from more distant sources, and NASA notes that this effect can be used to find isolated black holes that are otherwise invisible. This is especially exciting because many black holes may not be actively feeding and may not have a bright companion star. Such quiet black holes are much harder to detect. But if one passes in front of a background star, its gravity can magnify and distort the background light. If astronomers measure the event carefully enough, they can estimate the mass of the invisible lens. In this way, a black hole can briefly reveal itself not by emitting anything, but by bending someone else's light. It is one of the cleanest examples of gravity serving as its own detector. Then there's the method that changed black hole astronomy forever: gravitational wave detection. LIGO explains that some of the strongest gravitational waves are produced by cataclysmic events such as colliding black holes, and its public materials note that the historic detection in September of 2015 came from the merger of two massive black holes. This was a profound shift. Until then, black holes had been studied mainly through electromagnetic signals or through the motions of surrounding matter. Gravitational waves opened a new channel. Now astronomers could detect black holes even when no light at all was produced in the merger. The black holes announced themselves by shaking space-time, and detectors on Earth recorded that ripple directly. It was not merely another confirmation. It was a whole new sense for astronomy. This matters because gravitational wave detections do more than prove black holes exist. They reveal masses, merger histories, and populations that are difficult to study by other means. Some merging black holes might have been almost impossible to identify with telescopes alone. But in gravitational wave data, their inspiral and collision leave a pattern that can be modeled and compared with relativity's predictions. LIGO's more recent summaries make clear that black holes have become central sources in this new branch of astronomy. So detection is no longer limited to watching matter around black holes. Sometimes the black holes themselves, through their motion, become the signal. Perhaps the most famous method for the public is black hole imaging with the Event Horizon Telescope. This did not mean photographing the black hole itself in the ordinary sense. NASA and the EHT collaboration both explain that what was imaged was a bright ring of hot gas surrounding a dark central region. often called the black hole's shadow. The shadow is produced because strong gravity bends light around the hole, and because photons from within the event horizon do not escape. The result is direct visual evidence of a black hole's presence and of how light behaves in strong gravity near it. The EHT image of the black hole in the galaxy Messier 87, and later the image of Sagittarius A star in the Milky Way, were therefore not simple snapshots. They were reconstructions from a global radio telescope array, built from enormous amounts of data and careful modeling. Yet they provided something extraordinary, a way of seeing the outline of an invisible object by the glow around it. Even polarization measurements near black holes add to detection and interpretation. The Event Horizon Telescope has reported polarized views showing organized magnetic field structures close to black holes, including at the edge of Messier 87's black hole and later near Sagittarius A star. These observations do not merely decorate the image. They help astronomers understand the plasma, the magnetic environment, and the conditions that may launch jets. Detection is therefore not a single moment of recognition followed by silence. Once a black hole candidate is established, different observing methods continue to refine what kind of black hole it is, how it feeds, how it spins, and how it shapes its environment. What makes black hole detection so convincing today is convergence. No single method stands alone anymore. Astronomers can watch stars orbit hidden masses, measure hot gas in accretion disks, examine broadened spectral lines, detect X-rays from infalling matter, observe lensing events, record gravitational waves from mergers, and in a few cases even image the shadow region itself. Each method has limitations, but together they point to the same conclusion. Black holes are not accepted because of one dramatic picture or one elegant equation. They are accepted because the universe keeps behaving as though black holes are there, across many different wavelengths and many different kinds of measurement. There is something beautiful in that kind of knowledge. We do not always understand reality by staring directly at it. Sometimes we understand it by the traces it leaves, the motions it causes, the light it bends, and the silence it imposes. Black holes taught science to become patient in that way. They remained unseen, and yet they slowly became undeniable. Perhaps that is part of their deeper lesson. The universe does not reveal all truths in the same language. Some it gives in brightness, and some only in influence. And as you let that thought settle, there is a quiet comfort in knowing that even the darkest things in existence can still be known if we learn how to listen carefully enough. Chapter 9: Supermassive Black Holes and the Centers of Galaxies. Not all black holes are the remnants of dying stars. Some belong to a far larger and more mysterious class, supermassive black holes, the giant dark objects that sit at the centers of galaxies. NASA explains that these black holes have masses above about 1 million suns, while ESA notes more broadly that supermassive black holes are found at the centers of galaxies and can become bright when they actively accrete matter. They are not simply bigger versions of stellar black holes in a casual sense. They occupy a different astrophysical role altogether because they are woven into the structure, history, and behavior of entire galaxies. This is one of the most astonishing facts in modern astronomy. At the core of many galaxies, including our own Milky Way, there is a compact object of extraordinary mass concentrated into an incredibly small central region. In the Milky Way, That object is Sagittarius A star. ESO and ESA both describe it as the supermassive black hole at our galaxy's center, with a mass of about 4 million suns revealed through the motions of nearby stars. Those stars do not wander randomly. They follow precise orbits governed by an unseen but extremely concentrated central mass. That is one of the cleanest reasons astronomers are so confident about what lies there. The evidence from the galactic center is especially powerful because it is so direct. Over many years, astronomers tracked stars moving on tight ellipses around Sagittarius A star. ESO reported that these stellar orbits provide the best empirical evidence that the mass concentration at the center of the Milky Way must be a black hole beyond reasonable doubt, while later ESO work continued to trace stars even closer to that central object. This means our own galaxy serves as a nearby laboratory for studying the gravitational influence of a supermassive black hole in unusual detail. But the Milky Way is only one example. Supermassive black holes appear to be common features of galaxies across the universe. ESA materials on black hole observations note that supermassive black holes are found at the centers of most galaxies, and NASA's recent Webb explainers describe active galactic nuclei as active supermassive black holes that emit jets and winds and shape their host galaxies. That phrase is important. These black holes do not simply sit quietly at the center as passive gravitational anchors. When they are feeding, they can profoundly affect the galaxy around them. For a long time, the existence of such enormous black holes raised a difficult question. How did they get so big? A stellar black hole can form from the collapse of a massive star, but that pathway alone does not obviously explain monsters millions or billions of times the sun's mass. NASA notes that supermassive black holes must develop and grow very differently than stellar mass black holes. Astronomers think they may grow through prolonged accretion of gas, through mergers with other black holes during galaxy mergers, or through some combination of these processes, beginning from early seed black holes in the young universe. The full story is still an active area of research, which is one reason supermassive black holes remain so scientifically compelling. What makes them even more interesting is that they seem to grow together with their galaxies. NASA's Dissecting Supermassive Black Holes materials explain that these central black holes can sip or gulp gas and dust from surrounding disks, and that the resulting outflows can affect star formation both locally and farther away. ESA likewise reports that winds from actively feeding supermassive black holes can sweep away interstellar matter and shape their host galaxies. In other words, the relation between galaxy and black hole is not one way. The galaxy feeds the black hole, but the black hole can also regulate parts of the galaxy's future by heating gas, driving winds, and making star formation easier in some places or harder in others. This idea is often called feedback, and it has become central to galaxy evolution. If a galaxy's central black hole is actively accreting, it can produce radiation, jets, and outflows powerful enough to disturb gas on much larger scales than the black hole itself. That matters because stars form from cold gas. If the black hole heats that gas or blows part of it outward, star formation can be reduced. NASA's Webb materials and ESA's XMM Newton results both highlight this picture of supermassive black holes influencing the availability and state of star-forming material. So although the black hole occupies only a tiny central region, its influence can extend across a large fraction of the host galaxy. This helps explain why astronomers take active galactic nuclei so seriously. An active galactic nucleus is not simply a bright point at the center of a galaxy. It is a sign that the central supermassive black hole is currently feeding. NASA describes active galactic nuclei as active supermassive black holes that emit bright jets and winds and shape their galaxies. When viewed across the electromagnetic spectrum, these regions can outshine much of the rest of the galaxy. That brightness does not come from the black hole itself, but from the hot matter spiraling around it and the energetic structures associated with accretion. The center of a galaxy can therefore become one of the most luminous and dynamic places in the entire observable universe. Quasars are among the most dramatic examples of this phenomenon. They are powered by supermassive black holes that are accreting matter at extraordinary rates, especially in the earlier universe. Although this chapter is not centered on quasars alone, they reveal something essential. A black hole can be dark in itself, yet the environment around a feeding supermassive black hole can radiate with tremendous intensity. This is one of the reasons the centers of galaxies are so important observationally. They are not merely hidden cores. They can become visible beacons across enormous cosmic distances. NASA's Webb black hole science materials emphasize that different flows, winds, and jets from active supermassive black holes are key to understanding where the energy comes from and how it affects the host galaxy. Our own galactic center shows a quieter version of this story. Sagittarius, a star, is comparatively dim right now, at least compared with an active quasar. ESA describes the heart of the Milky Way as tumultuous and notes that Sagittarius A star is responsible for some of the action there, even though it is not currently feeding at the rate seen in the brightest active nuclei. That distinction matters because it reminds us that supermassive black holes can have different lifestyles. Some spend long periods in relative quiet. Others enter active phases in which they rapidly accrete matter and dramatically reshape their surroundings. The center of a galaxy is therefore not a static scene. It can change over cosmic time. Another reason these black holes matter is that they help test gravity in extreme conditions. ESO reported the detection of relativistic orbital precession in the motion of a star around Sagittarius A star. And other ESO work has continued refining measurements of stars in the galactic center. These observations do not just confirm the black hole's existence, they also test general relativity in a strong gravitational environment. So the center of our galaxy is not only a place where matter gathers around a supermassive black hole. It is a natural laboratory in which some of the deepest ideas about gravity can be examined. There is also a broader cosmological question hidden inside all of this. Galaxies are some of the largest long-lived structures in the universe, yet many seem to carry at their core a compact dark object whose size is tiny compared with the galaxy itself. That contrast is hard not to notice. The black hole is central but small, dark but influential, silent but capable of driving enormous outflows. It does not dominate the whole galaxy by volume, yet it can help set the conditions under which the galaxy evolves. NASA's and ESA's descriptions of black hole feedback make this point indirectly but unmistakably. The fate of a galaxy is partly tied to what happens in its core. In that sense, supermassive black holes are not just astronomical curiosities added to galaxies after the fact. They appear to be part of the larger story of how galaxies become what they are. Their growth, Their feeding cycles, their winds, and their jets all feed back into the environments that surround them. Even when the exact details remain uncertain, the broad picture is now difficult to escape. A galaxy is not only a collection of stars, gas, and dark matter spread across vast distances. In many cases, it is also a system whose center contains one of the most extreme objects nature can produce. There is something quietly humbling in that image. Entire galaxies can whirl for billions of years around a center that is almost invisible, as if vast luminous structures depend in part on a darkness they cannot outshine. And perhaps that is one of the gentlest reflections black holes offer us. The heart of a thing is not always the brightest part of it. Sometimes the deepest influence comes from what cannot be seen directly, only understood through the patterns it shapes across everything around it. Chapter 10: Hawking Radiation, Information, and What We Still Don't Know. By the time we reach this final chapter, black holes have already changed shape several times in the mind. They began as consequences of gravity, then became the end states of stellar collapse, then the engines of violent accretion, the centers of galaxies, and the objects that bend time itself. But black holes also lead to a deeper problem, one that sits at the border between the two great frameworks of modern physics. General relativity describes black holes as objects from which nothing can escape once it passes the event horizon. Quantum theory, however, describes a universe in which empty space is never truly empty and where information is not supposed to vanish from physical reality. When those two ways of thinking are brought together, black holes stop being only astrophysical objects and become tests of the foundations of physics itself. The first great shift came from Stephen Hawking in the 1970s. Using quantum field theory in curved spacetime, Hawking found that black holes should not be perfectly black after all. Instead, they should emit radiation with a thermal character. In classical relativity, a black hole can absorb matter and energy, but does not emit them from inside the horizon. Hawking's result changed that picture. It suggested that quantum effects near the horizon allow black holes to radiate as if they had a temperature. That was revolutionary because it connected black holes with thermodynamics and implied that a black hole could slowly lose mass over time. Hawking's original paper and later summaries of black hole thermodynamics make this point clearly. Once quantum effects are included, a black hole is no longer a purely one-way object. This radiation is usually explained in popular language through particle pairs appearing near the event horizon, though that picture is only a simplified aid rather than the full derivation. The more careful statement is that quantum fields in the curved spacetime around a black hole lead distant observers to detect a flux of particles with a thermal spectrum. However one chooses to picture it intuitively, the consequence is the same. A black hole can lose energy. If it is not gaining mass from infalling matter faster than it radiates away, then over immense timescales, it should shrink. The smaller it becomes, the hotter it becomes, and the faster the evaporation proceeds. In principle, if nothing interrupts the process, the black hole could eventually disappear. For real astrophysical black holes, this effect is expected to be extraordinarily faint. Stellar mass and supermassive black holes are so cold in Hawking's framework that their radiation would be overwhelmed by their surroundings, including the cosmic microwave background for ordinary isolated cases. That is one reason Hawking radiation has not been directly detected from astrophysical black holes. The prediction is widely taken seriously because it arises from well-established theoretical methods, not because we have watched a real black hole evaporate. There have been analog experiments in other systems that imitate related horizon-like effects, and those help illuminate the physics conceptually, but they are not direct detections of Hawking radiation from astronomical black holes themselves. Once black holes are treated as thermal objects, another astonishing connection appears. Black holes seem to have entropy. This insight grew from the work of Jacob Bekenstein and Hawking and became the foundation of black hole thermodynamics. In this framework, black holes are not merely gravitational traps. They behave like thermodynamic systems with temperature and entropy, and their horizon area plays a role analogous to entropy in the classical laws of thermodynamics. This is one of the most profound clues in all of theoretical physics because it suggests that gravity, quantum theory, and statistical physics are entangled at a deep level. The horizon is no longer just a boundary of no return. It begins to look like a place where microscopic information about the underlying degrees of freedom of space-time may somehow be encoded. And this is where the information problem arrives. In quantum mechanics, the evolution of an isolated system is expected to preserve information. The details may become scrambled, distributed, or practically impossible to reconstruct, but they are not supposed to be fundamentally destroyed. Hawking's original semi-classical calculation, however, seemed to say that the outgoing radiation is thermal in a way that depends only on a few macroscopic properties of the black hole, not on the detailed structure of whatever fell in. If a black hole forms from a rich physical state and then evaporates completely into featureless thermal radiation, where did the information about the initial state go? That apparent conflict between black hole evaporation and quantum unitarity is what became known as the black hole information paradox. This paradox is not just a technical annoyance. It threatens the consistency of the theories physicists trust most. If information is truly destroyed, then some cherished principles of quantum theory may need revision. If information is not destroyed, then Hawking's original semi-classical reasoning must be incomplete in a crucial way. Over the decades, many possible resolutions have been proposed. Some suggest that information does emerge in the radiation, but only through delicate correlations not visible in the simplest thermal description. Some propose that information is retained in long-lived remnants. Others explore whether it is encoded on or near the horizon in ways related to holography. More recent developments involving the page curve and island prescriptions have strengthened the case that a unitary picture may be recoverable in certain models, but there is still no single experimentally confirmed, universally accepted final solution for real astrophysical black holes. One reason the issue remains unsettled is that it lies exactly where our current theories are least complete. Hawking radiation is derived using quantum fields on a classical space-time background. That is already an approximation. A full theory of quantum gravity, which would describe space-time itself in quantum terms, is still incomplete. Black holes therefore force physicists into a difficult territory. We have enough theory to see the paradox, but not yet enough to resolve it beyond doubt. The singularity, the ultimate fate of evaporation, the microscopic origin of black hole entropy, and the exact encoding of information all point toward physics deeper than either classical general relativity or ordinary quantum field theory by itself. In that sense, black holes do not merely contain mysteries. They generate them in a structured way. There are other unresolved questions too. We do not know whether primordial black holes formed in the early universe in meaningful numbers, though such objects are sometimes discussed in connection with Hawking evaporation, because small black holes would radiate much more strongly than large ones. We do not know exactly how the final stage of evaporation behaves, because semi-classical methods are least reliable there. We do not know whether the horizon should be thought of as smooth in every relevant quantum description, or whether ideas such as firewalls capture part of the truth or not. We do not yet know the full microscopic meaning of black hole entropy. Even when recent theoretical advances look promising, they often emerge in idealized settings rather than directly observable astrophysical ones. So this last chapter is not a tidy conclusion. It is a map of the edge. And yet, that uncertainty is not a weakness in the subject. It is part of what makes black holes so valuable. Few objects in nature have done more to reveal where our understanding is powerful and where it breaks. Black holes confirmed relativity in extreme regimes, connected gravity with thermodynamics, and exposed tensions between space-time and quantum information that still define modern theoretical research. They are among the rare places where physics does not merely explain the world, but discovers the boundary of its own current language. That is why black holes remain so central to fundamental science. They are not just things to be observed. They are questions given gravitational form. There is something almost tender in ending here, at the point where knowledge becomes honest about its limits. Black holes began in this series as objects of collapse and darkness, yet they have led us into some of the brightest questions human thought can ask. They suggest that even the places that hide the most may still be guiding us toward deeper order. And perhaps that is the quietest reflection of all. The universe does not become less meaningful where our theories run thin. It simply invites us to listen more carefully and to accept that mystery is not the opposite of understanding, but sometimes its next horizon. And now, my friend, as this journey through black holes comes to an end, I hope your mind feels a little quieter and your body a little lighter. If you're still awake, you can stay with me and choose another peaceful science journey. And if sleep is already close, then I wish you sweet dreams among the stars.